Okay. After covering unfolding, now we move to another technique which is just opposite of unfolding. It is called folding. These names are very interesting. Here in unfolding, what we did, we paid in hardware, we parallelized, but system was slow, but still we could process input and output at a faster rate. So, input output rate could go up because we tried to retime the circuit first, the DFG first, we could go up to some level. Beyond that, maybe retiming was not helping. Then we tried to parallelize it, and by that process we showed that even though system is working at a slow clock, input output rate can be faster. That was unfolding. Here it is opposite. We try to gain in hardware and lose in speed as an outcome. That is, instead of using so many hardware units, maybe say adder, so many adders in the circuit, why not use one adder or two adders and do the job of all the adders in the circuit by using the minimum number of adders. Similarly, multiplier. Instead of using so many multipliers in different places in the circuit, why not use only one or two few multipliers and do the job of all the multipliers in the circuit by them in a time division multiplexed manner. That is important. Here, as you will see, the circuit has to be operated at a faster clock, because using say one multiplier you have to do the job of 10. So, using a faster clock, in one clock you will do the job of multiplier 1, in another clock you will do the job of multiplier 2, like that. That is why system is working, will be working at a faster clock. So, you lose in speed, but gain in hardware and therefore power. To explain, for example, let us consider this, that suppose originally we have things like this. At nth watt clock, one data is coming an, maybe 16 bit or 8 bit, whatever. It is getting added with bn in the nth clock, result is added with another data ca, this is your result. Now, here you see we are using two adders. Okay. Suppose I want to use only one adder, okay, only one adder. Then what I will be doing, if suppose the clock period, the nth clock, this is the nth clock period. Okay, I will divide it into two because there are two adders. So, I will divide it into two periods. They are called system clock period now. System will be faster. So, this is 0th, this is fast. So, actually this will be 2nth, this will be this 2n plus 0, this is 2n plus 1. This I think must be obvious to you, because if you start the timing diagram this way, say 0th original watt clock, this we are dividing into two system clocks 0, 1. Then you have got fast, you are dividing into 2, 2, 3, dot, 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 then 4, 5. So, nth, so first is 0th is 0 and 1. Out of first system input clock, we are having two system clocks, system clock 2, system clock 3. Then if it is second input clock, from which we are deriving two system clocks, one is 4, another 5. So, even odd, even odd. So, in the case of nth, 2n plus 0, 2n plus 1. Now, what we will do is this, we will use only one adder, say, okay. But both the inputs will be switched. This will switch to an. An is coming, it is coming over the whole nth clock, it is appearing here. But this switch is operating at a clock period twice, at a clock period half of the input clock, okay, like this. If this total was the input clock period, now it is working, system is working at half the period or twice the speed. So, I will be touching this at 2n plus 0, though an is available all throughout the nth input cycle from here to here, I will be touching it during this half, okay, and during that time I will be touching bn. So, bn also I will touch at 2n plus 0. So, during this half 2n plus 0, I am doing addition of an and bn. Okay. So, I am taking, if t is the original clock duration, now it is t by 2, t by 2. So, clock period is half, speed is twice. Okay. original speed is 1 by t, now it is 2 into 1 by t. So, in one of the system cycles of shorter period t by 2, I add a n and b n, then the result comes, this result has to be added with c n, and then this result what I do, I move it here to other end of the switch comes back, the switch comes back here at 2 n plus 1. That is when I move to the next system cycle within the same nth input word cycle 2 n plus 1, that time it comes. So, what I have to do? I have to hold this result in a delay. So, in 2 n plus 0, in 2 n plus 0, I am adding a n and b n, result is coming out, I am storing here. It is not a single flip flop, it is an array of flip flops. It is a 16 bit line. If it's a bus of 16 bit, there will be 16 flip flops in parallel, a register say. Okay. So, in 2 n plus 1th cycle, this data comes up here. That means, this result, this output is available here at 2 n plus 1. Switch moves here at 2 n plus 1. Why 2 n plus 1? Because at 2 n plus 0 I added, then there is a delay. So, this result comes up at 2 n plus 1. This switch moves here at 2 n plus 1. This moves here at 2 n plus 1. Hold on. Okay. So, 2 n plus 1 a cycle, this intermediate result and c n they get added and the result comes out here. So, this result you can take at next cycle 2 n plus 2. So, you see I used only one adder. So, adder complexity has gone down. Of course, I am using switches which are marks, but here only 2 adders were replaced by 1 adder. I could have had 100 adders, still I could have used only 1 adder to replace all of them. Clock would have gone up by 100 times, but number of adders would have gone down by 100. Okay. And I would have used the signals in a time division multiplex manner. So, this is an idea of folding, one example of folding. I am folding 2 adder into 1 adder. So, folding factor is 2. 2 hardware units brought down to 1 hardware unit, and thereby the clock speed also went up by 2. In one of the clock period, which is the system clock period, which is 2 n plus 0th system clock period, I do one job, I do one job of the adder, or I do the job of one of the adder. In the other system clock, I do the job of the other adder. So, this is basically doing the job of both the adders in a time division multiplex manner, first at 2 n plus 0, then at 2 n plus 1. Okay. Let us now try to generalize this to a DFG. Suppose in a DFG, there are various nodes, u, maybe u prime, maybe u double prime, dot 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 dot. They are all of the same type, same type of hardware. For example, they all could be adders. Okay. This has a separate input line, this has a separate input line, this has a separate, and like that. This can go to various other nodes, this can go to various other nodes, and like that. All right. I want to replace n is an integer, n of these nodes by one common hardware unit. Okay. Of the, we can say U type, U means U category, U prime, U double prime, they are all coming under the same type of hardware. If it is a adder, then U category will be adder. If it is a multiplier, U category will be multiplier. They are all named like in terms of U, U prime, U double prime, U triple prime, dot dot dot. Just various nodes, but they employ the same hardware. I am just identifying them. Out of them, I am taking capital N of them, okay, and replacing by 1. 1 means what? One hardware unit of the U type. See, if original U was adder, so capital N adders, all of them are adder, capital N of them I replace by one adder. Okay. So, basically I will have one hardware unit H of the U type, and what it will do? There are data lines, okay. One may be for, if you can call it data line, you can call it say data coming here, you can give it a name small u n, this is u prime n, this u double prime n, like that. So, here also same u n, u prime n, next maybe u double prime n, the same data lines. So, they are coming at a original input clock, that is original input clock may be like this, nth. But what I am doing, I am using a switch like a commutator, it will move. It is not necessary that ordering will be like this, that u n first, then u prime, u double prime. Ordering will be up to you, that is called scheduling, who first, who next to next, like that. I am just showing an example that this will start at u n, going to u prime n, u double prime, but then ordering can be changed. So, what will happen? The original clock will be now divided into small sub clocks. Each is a system clock. So, this will be how many? Total n, okay, capital N. So, if you see the timing diagram wise, 0th input clock, that will have capital N number of system clocks faster. So, I can index them, the 0th, first, just there will be a time period, clock period around that 0, around 1, I am just indexing them, 0th, 1, 2, dot, n minus 1. Then first, it will be from n plus 1, dot, to n minus 1. So, in general, nth, small nth original clock, that is input clock, that will start at what? N into n, okay, n into n plus 1, dot, n into n plus n minus 1. So, in one of these clocks, this switch will touch one of the input lines, in next clock it will touch another of the input lines, and like that. Okay, so, data here will enter at a faster rate. So, if original clock period was capital T, it will be now T by n at a faster rate. Okay, it will give the output. So, in one of the clocks, it will take up the job of say u. So, that time the output will be going along this line. So, this should go to those directions. Next time, if it takes up u prime n, next clock, that time this output line should work like these two lines, these lines. It will give the data to those nodes. So, those things have to be incorporated. Okay. So, now with this, what I do, suppose in the DFG, out of all the various U type of nodes, U, U prime, U double prime, dot, I pick a particular U, and suppose there is an edge from U to another V. Okay. V also has its, V can be an adder again, there can be multiplier, can be divider, can be some. Okay. So, V also has got various nodes, like V, V prime, V double prime, dot. They may not be same in number, but V also has various copies of the same hardware unit, maybe multiplier, one multiplier, another multiplier, another multiple, like that. They are all taking input from different lines, different nodes. Now, when it comes to U, particular u and particular v from here, I find that in the DFG there is an edge between them with some delay w. This delay is with respect to the original clock. Original clock is slower, system is faster. In one original clock period, there are capital N number of system clocks. Okay, one that we have seen already. In any original clock period, I have got capital N number of system clocks. So, W number of input clocks means W into capital N, that many system clocks. Now, what happens after, how to unfold this, how to fold this, or in a folding situation where I am taking u, u prime, u double prime, dot 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 all of them, capital N all of them, replacing them by one hardware unit of the u type and working out a time division multiplexing like this. So, a particular clock, this will take up the job of u, okay. Then it will do the processing, then output should go to v, not v prime, not v double prime, okay, after some amount of delay. How delay? Originally w input cycle, now what? That is what we will find out. Okay. So, suppose in the ns cycle, at n capital N may be plus small u, that time, that is this time, at that clock h u takes up this data u n, that is at that means small u can be either 0, one of the points, or 1 or dot 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 up to this. So, in the figure it is general, in the general case put here. So, at n n plus u, that time this switch touches this, means that time this hardware unit will take up the job of u, because then it is taking, because the input u n is touched then by this hardware unit. So, it will then, that means it will take up the job of u, not of u prime, u double prime at that system clock. By the way, since this hardware unit now is working at a faster clock, it is often necessary to minimize the critical path of the device here, maybe adder, multiplier, whatever, by doing some pipelining. Pipelining means I will have forward path pipelining, say I will have some pipelining latches. Okay. Like I will do cuts and retiming, forward path, I will introduce delays, that is in general, so that critical path reduces here, this device can work at a faster rate. So, if that be, then there will be delays to, just a minute. This is suppose the hardware unit, say adder or say multiplier. Okay. I should do forward path cuts and retiming and introduce delays between them, so that critical path reduces. Okay. Because why it is necessary? Because here system is working at a faster rate. So, the original critical path of the hardware unit may not be short enough for processing of data at that rate. So, it may be necessary to do some pipelining by forward path cuts and retiming. So, there will be some delays coming in, which means input will be delayed. Output here will be delayed version of original output, because I will be introducing delays in this hardware. What for? The delays will be doing forward path retiming or forward path pipelining. That is, this stage will be divided into, like as we told you, if this is u, it will be divided into various stages, and between every two stages there will be a delay, between these two stages there will be a delay, like that, pipelining. So, data coming here will not appear here in the same cycle, it will go through various delays. So, it will appear after some number of cycles. So, just for counting purpose, I show that number of delays separately. Here P for pipelining, U for U category, Pu is an integer, maybe 2, maybe 3, maybe 4, that times D. If it is 4, 4D, that means 4 delays will be used to pipelining this, which means even if an input comes, corresponding output will not be the original output, but it will get delayed here by 4 cycles, then only it will be coming here. Okay. Why we need it? As I told you, system is working at a faster clock, so we may often need to pipeline it, so that it can process data at that rate, That is why some delays for forward path pipeline will come up. Those delays we are collecting separately for counting purpose only. Pu is an integer. That very number of delay is used to pipeline it. These delays we are showing separately. Okay. So, this is the situation. So, this small u n into capital N plus small u, a particular system clock within the nth input clock. It is denoted by n into capital N plus small u. If u is 0, we are here. If u is 1, we are here. In general, u is here. U is called, the small u is called schedule of whom? That node u, whose input is u n and it is touching there at n n plus u. Similarly, in another timing diagram, under the same nth, sorry, we will have n n and dot dot dot, maybe at n n plus some small v here. Okay. One hardware unit I will be using to take capital N of this v category and replace them by that. That is, let me explain. This is for u. Similarly, for v also, say hardware unit is of the type HV. Maybe this is an adder, this is a multiplier. But both can be adder. Maybe there are 10 adders, 5 I am taking here, 5 another 5 here. Okay, all are possible. So, but anyway, this is HV, and again this is pipelined by PV number of delays. I am showing one input here, there can be multiple inputs, taking data from multiple directions. Okay. This is HV, this is the thing, and again if this is small v n, if this is v prime n, this is v double prime n, here also maybe say v n, v prime n. So, capital N number of such nodes I replace by one hardware unit of the v category. If it is a multiplier, this is a multiplier with some delay coming due to pipelining. Okay. And it will touch this line once, it will touch this line once, and like that. I am designing the schedule of node v to be small v, that is n n plus 0, n n plus 1, at n n plus v, small v, that time I am saying this will touch this line. That means input will be v n, so this will work for this v. They are scheduled digits. Small v could have been 0, could have been 1, could have been 2. I am writing a general case. So, we have done this for u, we have done this for v. Why u and v are important? Because there is a particular edge coming from node u, specifically node u, not from u prime, not from u double prime, specifically from u and specifically to v, not to v prime, not to v double prime, but specifically to v. But in my folded setup, I do not have separate u, I have only one hardware unit which does the job of many of the u type of processor. One of them is capital U, of course, and it is doing that job at n into capital N plus small u, okay, somewhere here. Similarly, I do not have, I mean, even if there is a node v here, I do not have separate node for v here, but out of I take capital N of the v type of nodes replaced by one unit. Okay, it is touching various input lines at n n plus v, it is doing the job of that. All right. Then how much delay I should have. Originally, I had W number of input delays, input cycle, because that is what is given with respect to input cycle. Folding is my creation, but this node, this DFG is given in terms of original input. Okay, I have got W number of delays, all right. So, that means in the timing diagram, I can erase this timing diagram down, or maybe I draw here separately. From nth, this is n plus 0. I am interested at n plus u. I am starting at u first. So, okay, at that system clock, the data enters, okay, goes through this process. After being processed by the u category, it has to be delayed by W number of input cycle. Now, one input cycle has got capital N number of system cycles. So, W number of input cycle means W into capital N, that many, W into capital N, that many system cycles. So, it will come under some other node, other umbrella. Okay. If it is small nth, it is small n plus wth. So, gap between them is W number of input cycle, which means W into capital N, that be number of system cycle. So, you are starting at small uth. If you go by capital N, you enter the next, but reach the same small uth point, okay, because it is periodic in capital N. When you jump to the right by capital N, if you start at small u, here also you go to small u. Okay. If you are jumping by Wn, so here again you are coming at this much is Wu, u. Okay. But so this is coming after this W number of input cycle, this is coming here. Okay. But schedule of V, that is, it is not taking up the job of V category at this specific point. It is doing maybe further to the right, this much may be V. That means, even if after getting processed here and then getting delayed by Wn, it has come here. You understand, it will be again, if this is small u, if this is small u, this also small u, because you are jumping by an integral multiple of capital N. If you jump by capital N, 2n, 3n, whatever, you will hit the uth point only, so u. But then that is not the point where in general this hardware unit is taking up the job of V, because I am interested specifically in V. Maybe its schedule n into capital N plus V, that is V, is further to the right. That means I have to have further amount of delay of V minus u, if V is greater than u. Okay. That means delay, this output should have a delay, how much? Wn plus V minus u. Now, out of this delay, already a Pu amount of delay has gone in. So, net delay required will be minus Pu. Then here, if you tap, that is tap at that point, n in small n into capital N plus V, if you tap it here, you will get what you are getting here. Then you can happily give it to this. All right. That means, if this u has u category, u node has got schedule small u, V node has schedule small v, and they are chosen by you fixed. Then after this processing by you should have a delay of this much amount, okay. So that when you touch this at the schedule small v, that is at n into capital N plus v, okay. It may not be n small n, it may be some other unit, just a minute. because it's coming delayed, it's coming after some delay. So, if you touch it at some other point, maybe some m for some integer n, m into n plus v, m is actually very simple, a small n plus w, okay, because it was nth, so it become n into capital N. This is n plus wth, because after this it has to be delayed by w cycle, w input cycle. So, n plus w. So, m is n plus w, that is what I wrote, n plus w. That times n plus v, as I tap, I will get back what I was getting here. So, this is the delay that is required, and this we denote by this p u to v. Okay. Or maybe there is another notation, let me switch over to this is an old notation, better will be D. This is what Paris book does, D for delay, F for folding. After folding, with respect to the faster system clock, delay between U and V will be this much, because after folding you do not have separate U node, separate V node. There is a hardware unit, it is sometimes working for U node U, there is a hardware unit, it is sometimes working for node V. So, I find out when it works for node U, I design a schedule. So, n into capital N plus small u, that is the time data comes from small u n, which means this hardware unit is taking up the job of U node only. So, it does the processing. If all are added, this is an adder, but goes through some delay because of pipelining. After that, I have to hold it, I have to pass it through W number of input delay, which means W into capital N number of system cycle delay. W number of input delay means from nth it will go to n plus wth, which is mth. Okay. So, that means in terms of input cycle is W into capital N, that many times system cycle. So, from uth point, here again under another umbrella I go to the uth point, but a schedule of capital V may not be U, may be V. If V is larger than U, then another additional time V minus U times I have to wait further. So, additional delay required, out of which PU goes, because PU already has been implemented. Because small v could have been here this much, I mean instead of this it could have been less. So, V minus U is negative, which means I do not need so much of delay, I need less than that. How much less? V minus U. So, from Wn something will be subtracted, so that I am here. Whatever is V minus U, or you can write V minus U equal to minus of U minus V. So, U minus V, this much will be subtracted from Wn. So, you are here, out of which Pu will go. You only need to make sure that this is not negative, because there are minus signs. Okay. So, you have to make sure that your schedules are designed such that it is never negative. We build upon this in the next class. Thank you.